Now, do you remember what the inverse of a function was? Well, we looked at it a couple different ways. One, we remember that any function that was one-to-one had an inverse. And likewise, if it passed the horizontal line test, if we saw its graph, we would also notice that it would be one-to-one and therefore have an inverse. Basically, the inverse is just a reflection of the graph about the y equals x axis. So as we're looking at trigonometry, do some of our trigonomic functions like sine have inverses? Well, I have the inverse wave or the inverse graph part of it here right now. Is that an inverse or can it have an inverse? No, you're right. And why not? Well, it is because we're noticing that I have a horizontal line that intersects the graph in more than one spot. And when it does that, by definition, it is not one-to-one and doesn't have an inverse. So what do we do? Is there a way to kind of look at some of the information from an inverse or an inverse sine in some type of way? So what we do in that case is we do, but we restrict the graph, which means that we look at a segment of the graph, for example, from like negative pi halves to pi halves. Within that domain restriction, we notice that the graph appears to be one-to-one. There's no spot on that graph where our horizontal line crosses at two places or more from negative pi halves to pi halves. So what we'll do then is we'll look at just that aspect of this graph and look at its inverse on a restricted domain. So let's look at a couple more ideas and expound this a little bit further. So what I've done here is I've taken the part that we've been talking about between the domain from minus pi halves to pi halves and kind of stretched it out a little bit and just focused on that one area. So notice then that it does obey the horizontal line test. There's no spot on this graph where a horizontal line intersects the graph in more than one place. So if we restrict the domain, now we can look at its inverse of this particular sine function. And there's two ways that we can kind of graph its inverse. First, if we start with the original graph, the sine, we remember that inverses were the same coordinate points but just switched around. So rather than the point negative pi halves and negative 1, we would have the point, probably right about there, of negative 1 and negative pi halves. So that point is on the inverse of the graph. Likewise, pi halves and 1, its a and b, or its x and y coordinate. This inverse is going to be inversed. And so we would have the point 1 and pi halves. Remember, that's what inverse means. One way it means is that you take their coordinate points and reverse them. And then we know the inverse of 0, 0 is still 0, 0 as well. So we can draw a smooth graph that goes through those particular points. Another way that you can also do it is notice that inverses are all symmetric about the y equals x line. So if I drew a graph that was symmetric with this blue one, and I also got some points that kind of help me here, there as best as I can, I have graphed the inverse of sine. So again, what we're looking at is the sine graph itself does not have an inverse. It only has an inverse when we restrict the domain and range, or we restrict the domain of the sine graph. Then that we're able to produce its inverse. We can also look at the domain and range of those. So the domain of its inverse are all my x coordinates, which is from negative 1 to positive 1, and its range is from negative pi halves to pi halves, based off of the restricted sign that we begin with. All right, let's look at a couple more ideas and a couple more thoughts before we explore some problems with these. So how do we denote what an inverse looks like? Remember the notation in a standard function where we had some f of x, x just being the chosen variable? We would denote the inverse as an f with a little -1 in the subscript right there. And it would be inverse of x. So function of x, the inverse of that function of x. With sine of x as our normal function, we would write its inverse such as this, such that we have the -1 just a little bit above the n and before the x. And then some people will also use a notation that says arcsine, Both of those are the two most frequently used in standard notations for the inverse of a sine function. It's also an idea to kind of remember this idea too. Does this equal the 1 over sine of x? Is it a reciprocal? Because remember, when we have a negative in the exponent, we're able to make it a positive by flipping it down into the bottom. But no, that's not the case for this particular one right there. It would be if it was written this way. That is the description for the reciprocal of sine, which would equal 1 over sine of x, or it would equal, what is the reciprocal of sine? The cosecant of x. So keep in mind the difference between those two, just as far as the notation is concerned. The notation is something we want to get used to. So this represents the inverse of sine. It can be written this way or as the arc sine. If I have a -1 outside of the entire function, then that's the reciprocal of sine. Two different ideas. I want to find the inverse sine of root 2 over 2. So what does that mean? Well, first of all, this means that I'm looking for the angle whose sine is root 2 over 2. That's what the inverse is asking us, is we're looking for the angle whose measurement is root 2 over 2, or produces a root 2 over 2. So how do we do that? Well, first of all, we think about it in terms of angles. So I have some theta, which in this case would equal the inverse sine of root 2 over 2. What's the angle whose sine is root 2 over 2? My second step, I'm going to rewrite that in terms of the sine of theta using the definition of inverse. So the sine of theta equals my x value, in this particular case, root 2 over 2. And then from there, I'm going to look at my values, which I'm beginning to commit to memory, or I'm still looking at, and try to remember what was the relationship, what was the angle that produced a root 2 over 2. I have a values or a table that we're beginning to commit to memory over here, where my thetas are on the left, my sine thetas are on the right. So I'm looking at, where is root 2, 2? I remembered that it's right here. Root 2 over 2, the angle that produces that is a pi fourths. So my angle is pi fourths. And that's how we find the exact value of an inverse function. All right, let's do this one together. Well, no, let's don't do it together. Why don't you get a head start on it? What's the exact value of the inverse sine of -1/2? What are you going to do first? Well, let's think about it in terms of what we're trying to find, or what this means. Remember what it means? It means what's the angle on our interval that produces a sine of -1/2. So theta equals my inverse sine, of -1/2. Rewrite this now as, what's the sine of theta? The sine of theta is a -1/2. So what is the theta that produces that? Over here, my sine of theta, I'm looking for the values where my sine of theta equals -1/2. What's the angle that produces that? It's right there. The angle that produced that was the measurement, or the angle, -pi6. So pi6, or -pi6, is my solution to the angle of this original inverse sine. What were we trying to do? We begin with an inverse and want to find the exact value of that particular inverse sine function. Basically, we were looking for what's the y value, or the second characteristic, and what's the corresponding other characteristic with that. Kind of working the problem backwards a little bit. All right, you all right? Take some more practice. Where you might be getting a little confused a little bit about is, one, we're looking at these values. Those are the ones that you can look up, or we're beginning to commit to memory. And then rather than trying to solve for the theta, or begin with the theta and solve for the sine of theta, we're going to begin with the sine of theta and solve backwards to find out what's the theta, what's the angle that makes that sine true.